All right, welcome back, everybody. We're continuing on in our discussion of duality, and having established a number of properties of the Fenchel dual, we're going to spend some time talking about algorithms in the dual. We'll have a number of different lectures on this topic. So let's remember where we are so far. So our primal problem is has this form that we've been talking about now for a few lectures. Minimize f of x plus g of ax. We've seen a number of different applications of this particular formulation. Obviously, we don't want to be limited to problems with just two functions, but this can capture many of them. And the key thing that this captures, this formulation captures, and the key reason we're calling it a decomposition is the fact that this really wants to look like f of x plus g of y subject to a constraint that y equals ax. And it was really using that we derived the dual. And again, what we derived last time was under the assumptions of strong duality, that strong duality holds. So for example, if we know that we have an interior point in the domain of f and g, in other words, if Slater's condition holds, then this is equal to the dual problem, which is maximize minus Fenchel dual of f, evaluated at minus A transpose z, minus Fenchel dual of g, evaluated at z. So at this point, I hope that everybody is comfortable in how you could derive this. And if not, I think you should spend some time just making sure that you can practice. So under assumptions of strong duality, these two are equivalent. So so what we want to know is, why would it be in our benefit to work on an algorithm in the dual as opposed to the primal? So in particular, what we want to understand, which is of course not going to be generically true, we know that the dual of the dual is a primal, so dual is not something just magical. We want to understand when could we gain a computational advantage by working in the dual. And when I say working in, I mean by maximizing the dual. And of course that implies that we have a method to go from a dual optimal solution, z star, back to a primal optimal solution, x star. And a few types of answers that we're going to see are that the dual could be may involve simpler computations. For example, we might have dualized the constraints, so we may have no constraints in the dual, and therefore things may decouple more. So hence, we might be able to exploit some additional structure. The dual might be smooth. So if we have strong convexity in the primal, then we saw in our lectures on Fenchel duality that the dual is going to be smooth. So what does that mean? In terms of gradient descent and rates of convergence, we know that if you have strong convexity but you don't have smoothness, the best that you can hope for is 1 over t, rate of convergence. But if you have smoothness, then with an accelerated method you can get 1 over t squared. So by that token, there are more algorithms that we can use in the dual. You could try to exploit smoothness in the dual. Or again, this is sort of similar to the first bullet point here of having no constraints. We might have some separable problem in the dual, but not in the primal. I mean, something might be separable in the dual, but it may lack separability in the primal. And typically, this will happen because of a norm. This will happen because of some kind of inequality or equality constraints. We're going to see a number of different algorithms in the dual. Primarily, it's going to be the suite of algorithms that we've already developed. So we're going to explore what is gradient descent look like. The dual, of course, is a maximization problem. So we'll either get rid of that minus sign and just talk about gradient descent, or we're going to talk about gradient ascent. We are also going to talk about an algorithm that is somewhat familiar to us from our discussions on proximal gradient, but it's going to play a bigger role for us now than it has in the past, called just the proximal point algorithm. And we'll see in detail what that is. And of course, we could combine these two and get the proximal gradient. And variance. So this is going to be much more interesting than just rehashing everything we've seen already in terms of these algorithms, because in many cases there is some expense in going from the primal to the dual. And in fact, the dual may not have a simple representation where we can now completely forget about the primal and just work in the dual. So the examples that we've seen were somewhat special because they had an analytic and closed form representation of the dual that we could just write down. But that may not in general be the case, and we're certainly not going to be limited to those situations. That would be extremely limiting if we could only apply these algorithms to the dual. So this transformation from primal to the dual is in a way going to be always with us, and it's going to be very intimately related to what all of these algorithms that I've listed or alluded to are going to look like in the dual. So let's have our first look at that right now and see what dual gradient ascent looks like. And let's specialize our formulation to a setting of where we have equality constraints. So just an example, we'll see various versions of this problem, of the general primal and dual problems in this series. So again, this means that I have minimize f of x subject to ax equals b. For the time being, I'm not going to place any additional special structure on f, but immediately you can see that if f was something that decoupled into blocks of variables, then the equality constraint ruins that decoupling. And so this is one of the primary reasons why you might benefit from dualizing. And we've already talked about in our series on Fenchel duality of how we dualize this and how this falls into our framework, namely our function g is just the indicator function of the single point b. And so if this is the primal, then the dual is maximize minus f star of minus a transpose z minus b transpose z. Again, this is something that I expect you can easily derive. And what's a gradient descent? In other words, what's gradient ascent? In this case, it's just zt plus 1 is equal to zt, not minus, but plus, because now we're following the gradient because we're maximizing. So plus our step size and an element of the subdifferential. Because I wrote gradient, I'm just going to put this in quotes here. The quote of the gradient of whatever this of this function here. So minus f star of minus a transpose z minus b transpose z. Okay, so now let's look at what this is. So I need a subgradient that's an element of the subdifferential. I'm writing it properly now of this thing minus f star of minus A transpose Z minus B transpose Z. We know how to write that. So this is equal to minus B plus, by the chain rule, A times something in the set, the subdifferential of f star of minus A transpose Z. So what we need is something in here. And let's write this as, so basically, let's write this as x hat. And so then we see that we have zt plus 1 is equal to zt plus lambda times a x hat minus b. And what we have left to compute is what x hat is. So x hat is an element of the subdifferential of f star of minus A transpose Z. And now all our work on properties of the differential dual is exactly what we're going to be exploiting throughout here. In particular, we showed that something is an element of the subdifferential of the differential dual if and only if minus A transpose Z is in the subdifferential of f evaluated at x hat. So in other words, x hat is an element of this if and only if minus A transpose Z is an element of the subdifferential of f, not f star, at x hat. This is exactly the same as writing that 0 is an element of the subdifferential of f at x hat plus A transpose Z, which is exactly the same as saying that x hat is a minimizer of over x of f of x plus Z transpose AX. So this is x hat. Now there's a lot to say here. First of all, we observe that just minimizing, just taking one step of the gradient algorithm in the dual actually requires us to minimize something that has f of x. So, generically this is not going to be necessarily easy. But on the other hand, we see that this minimization that we need for every single step of gradient ascent has no more constraints. And in particular, it's our original function plus something that's now linear in x. So in the example where f of x has this decomposability structure over blocks of variables, and the simplest case, let's just suppose that f of x is equal to the sum of fi of xi, then this minimization here will now decouple into d, if d is the dimension, single variable optimization problems. Much easier. And so this is the whole idea. So that's the first thing, that why this might be easier. The second thing to note is just to observe what has happened. So this sub-problem that we're solving is really just a Lagrangian problem. All I've done is I've just dualized the constraints. So note that because I'm looking at an argmin over x, note that I could easily just add in here minus Z transpose B. And so really what this looks like is minimizing the primal plus a penalty, Z, times your violation of AX minus B. So this should be familiar from the general derivation of duality where we dualize the constraints. So this is finally the algorithm. Let me just write it down one more time. So that means that gradient ascent tells me that zt plus 1 is equal to zt plus lambda times ax hat minus b, where x hat is an element of the argmin of the Lagrangian function, f of x plus z transpose ax. Let's keep going. Let's see a different type of problem here, and I want to look at a more explicitly separable problem, the one that I've been essentially referring to. So we've got minimize f1 of x1 plus f2 of x2. x1 and x2 are blocks of variables. So in dimensions d1 and d2, let's say, but there's no overlap. So that's what this notation means. And then I have a constraint that, in this case, just to have a little bit of diversity, I'm going to write an inequality constraint rather than the equality constraint. a1 x1 plus a2 x2 is less than b. And I write this squiggly less than just to make sure that we're not, it's clear that I don't mean that we are necessarily bound to the positive orthant. I'm not saying that b minus a1x1 minus a2x2 is in the positive orthant. That difference just belongs to some convex cone. And these are called coupling constraints, or sometimes they're called complicating constraints. Again, what our overall goal is in this story is to solve two simpler problems rather than one big problem. And the reason that that's a win is that solving a convex optimization problem is not linear in its complexity. Best case, it's going to be cubic in dimension, maybe fourth power in dimension if you think about complexity of solving LPs. So I would much rather, I have a much bigger win by solving 10 problems 1/10 the size each than solving one problem of the big size. This is a common, this kind of divide and conquer is prevalent everywhere. Linear algebra, which is really the core of optimization, has these types of, this flavor of algorithm as well. If you can invert two smaller matrices, you would much rather do that than invert one bigger matrix, just because inversion scales like the cube rather than linear. So this is straightforward things, and what we want to do. Okay, so let's write down the dual again. Let's call this the primal, and then the dual is maximizing minus f1 star of minus a1 transpose z minus f2 star minus a2 transpose z minus b transpose z, subject to, now I have a constraint on z. Again, it's very helpful to think back, at least for intuition, to linear programming. If I have equality constraints, like I did on the previous slide, then my variable is unconstrained. Here I have an inequality constraint, and so we expect my dual variable should be constrained. And again, I expect that you can derive this. And what did we use? We basically used calculus rules for the Fenchel dual, and our formulation that we had in the previously. So, you know, again, I expect that you can check this. Okay, so let's write down what the algorithm is. So again, just writing down the dual problem that I just wrote. This is minus f1 star minus a1 transpose z minus f2 star minus a2 transpose z minus b transpose z, subject to z. I'll just say greater than or equal to 0, but we really mean membership in the cone. And gradient ascent is zt plus 1 is equal to zt plus lambda, our step size, now times something that's in the subdifferential of the above. And what's in the subdifferential of the above? Actually, I need to project it as well. Right? So it's lambda times the projected gradient. So it's projected onto this cone of something that's in the subdifferential of the above. What's in the subdifferential of the above? Again, exactly the same mechanics that we had before. The chain rule is going to bring out a minus a1 and a minus a2. So I'm going to have a1 times x1 hat, where x1 hat is in the subdifferential of f star, plus a2 x2 hat. x2 hat is going to be in the subdifferential of f2, minus b. And writing this out, we see we get exactly the same mechanics. So x, as we did before, x1 hat is an element of the subdifferential of f1 at minus a1 transpose zt. x2 hat is an element of the subdifferential of f star 2 at minus a2 transpose zt. And exactly what we did on the previous slide, using the fact that subdifferentials of the function and differential transform are inverses of each other, we get that x1 hat is an element of the argmin of f1 of x1 plus z transpose a1 x1. And similarly with x2 hat, it's an element of the argmin of f2 of x2 plus z transpose a2 x2. And so we see this a little bit more more explicitly here. I have to solve two problems for every step of gradient ascent, but these problems have no constraints, and moreover, each problem is only in x1. So these are now decoupled. On the other hand, I haven't just overall decoupled the problem. I have to solve them at every step. This has another very convenient interpretation as price coordination. And it is the basis of many distributed optimization algorithms. The idea is simple. The idea is that you have agents that need to use a common resource. The common resource is where this original inequality constraint comes from. And agent 1 takes actions x1, agent 2 takes actions x2, agent k takes actions xk, and of course these can be blocks of variables in whatever dimension you want. And so the interpretation is that they choose an optimal solution, they solve their problem. That means each one of them reports an xi hat. So they send an xi hat back to some centralized agent. Xi hat goes up from all of these. And then the agent computes the new price. What's the new price here? It's going to be zt plus 1. And so you can see that zt plus 1 is exactly a function of all of the x's that you get. And so what goes back down is zt plus 1 computed and then broadcast. So rather than having to solve a centralized problem with many variables, you can let the agents solve individually. You don't even need to let them know what the other agents are doing. You just need to report back what is the price. If the resource is underutilized, that price is going to be 0. So this is the story here, and let's just see a concrete example of this. I want to minimize, say, a sum of quadratics in different variables, but with a coupling constraint. So I want to minimize the sum over I of a bunch of quadratics. 1/2 xi transpose pi xi. Again, xi is going to be a block of variables of dimension di. Doesn't even have to be the same. Plus qi transpose xi, subject to uncoupled constraints, a constraint on each one. Bi xi is again less than or equal to, and whatever is the relevant cone that we care about for our problem. And then one coupling constraint. Also sum of ai xi less than or equal to b. So I have one coupling constraint. And I'll leave this as an exercise for you to go through this. Compute the dual and compute what gradient ascent looks like. And in this case, in fact, you can do it explicitly because we know what these are going to be just quadratics. So I'll maybe add to the exercise of maybe compare to the naive complexity of solving the primal directly. Again, the reason why I'm saying I write naive is that you can never make a problem easier. We're just looking at our suite of algorithms and talking about which ones are more effective in which regime.